nice collaboration. And then we started to think, what about exchange students? What about research? And everything has evolved. And look here, this was a meeting 2011 with this number of students. There are Germans, there are Brazilians, and we just met every year. And I would just point some of them, so you remember me. I would like to, this guy here, and this one. So here he is, and this is the other one. And this is 2 years later, but then in Germany. Yeah? And because he was here, the parents of him were there as well. And from that it started like, you know, not only friendship, but really a personal contact to those people who are Germans. By the way, this guy was on the picture before as well. And this one is actually a Brazilian one. She was in Germany at that time, from the very beginning, being a child, and then studied there, and then went to Brazil here again, and started to work at INPE. And here, Mayra at that time was in Germany with Ciencias Sin Fronteras, so one of the best programs Brazil ever had, I think. And currently, yeah, that's she again. And currently, she is in my laboratory doing her PhD work. So it's a long time, and it's this is the last here some years ago, and this is exactly after Copa del Mundo, and this is exactly after this. Not allowed to say. Yeah, so instead of getting the 6 here for Brazil, Germany got the 4th. And therefore, if you everything is perfect, but exactly the motivation you will find in going abroad. And how it works after that, it's just like another life, it's just like another open other door and go through. So I can talk to you, to the students, to your colleagues. It's really a good thing to be there. Okay, if you look for scholarships, if you like to look for scholarships, if you want to know how to move in Germany, everything, is basically here. So DAD, which is in German the Deutsche Akademische Austauschdienst, or in Portuguese over there. And there is even a Portuguese office here located in Rio. They have this address here. So just if you take this one, dad.org.br, then you will get the link to the DAD as well. And there is a whole databases of scholarships and things like that for Brazilian, for others as well, for students, for researchers. But basically, you always have to think if structuring there a little bit, undergraduate, short-term, master programs, that's long-term, and research is something totally different. Okay, but they are serving. Thank you for your attention. Done. And you can browse. Any questions, maybe? It's not the case. Okay, we're on. Thank you.
Vocês teriam mais alguma pergunta para a professora Andressa, para mim e para o professor Zilk? Sim.
Professor Zilk, in your university, do you have some programs for arts?
No. No, it's just about technology, business programs like that. I'm sorry.
Nós estamos recebendo agora, dia 6, vai estar aqui dia 5 e vai retornar dia 7 de outubro, 2 professores da Universidade da Virginia Commonwealth University, VCU. Eles vão estar aqui, que deve ser a segunda universidade nos Estados Unidos na área de artes. Eu vou me reunir com estudantes, com eles, vão fazer uma programação no Centro de Artes e Letras, vão convidar o Centro de Artes e Letras, mas fica atento, dia 7 eles vão estar aqui e é uma grande oportunidade para a área de artes. Artes visuais, artes cênicas, na área de artes. Eu tive agora lá, é fantástico, é uma universidade integrada, deve ser a única nos Estados Unidos, integrada com a cidade, fica na cidade de Richmond, na Virgínia, e assim tem um prédio, um hospital de câncer, de não sei o que, do lado tem um barzinho, é extremamente integrado, não tem um campus. E a parte de artes deve ser a segunda, eu não sei, eles disseram que era a segunda nos Estados Unidos, eu nem sei quem é a primeira, deve ser em New York ou Califórnia ou coisa que vale. Tá? Mais alguma pergunta?
Well, the program of the school will follow. We'll start the classes late, but we'll start now until midday. So, thank you.
Obrigado pelo convite. E estamos indo. Eu só vou me despedir. Professor Zil, it was very nice to meet you. Thank you. Professora
doing nothing. Okay, so we start later, so but I will finish earlier now. Just tell you a little bit about software testing, okay? Testing and debugging. You ready?
Yes.
What comes first, testing or debugging? What is first? Debugging for, and then testing?
Yeah.
I think debug comes first.
Because debugging is a software that's not working properly, that you try to fix. And when
Okay.
you're testing,
So when do you debug? You debug if you know there's an error.
yes.
Okay, so first is the error and then is the debugging. You
Yeah.
try to find the error. What is the goal of testing?
Check that there is no error.
Oh, definitely wrong. You didn't miss the test. No, the goal of testing is to find errors. A successful test is, then you can say, I found one. It's difficult to understand, it's a destructive action. We don't like it because we think we produced a perfect part of software. And we have the feeling it's so great, there are no errors in it. But this is wrong. We know that people are quite clever, but they are not as clever that they have no errors in, let's say, 10,000 lines of code. There are errors in it. We have to accept that. So testing is the goal of testing. Okay. Motivation now. Then what is testing? Example for generating test cases, coverage, in the resume and literature. Okay, no motivation. Okay. Friends. Okay, I'm back. The motivation is software systems and programs contain errors. We have to accept that. You cannot show me, unless it is the 10 line of code, that there is no error in it. There are errors in it. We have to cope with it. It's nearly impossible to write programs without errors. Because there are so many things we have to think about. So many little faults, a minute of unconcentration and we have an error in it. Something you do not know. You cannot know everything. Some things you do not know and you have errors. So goal of good software development should be to keep the number of errors low. You can't get it to zero, but we have to try to get it as low as possible. This is the German version of the one above. And this one is interesting. There are errors in the software. We know that. And sometimes an error is occurring. So the results of the error should be as small as possible. Okay, if you have a calculation program like Excel, and there is an error in it, okay. Yes, you have to correct it. If you are in an airplane, the man in front of the airplane says, oh, we have an error here, and I cannot fly the airplane anymore because there's an error, then you should worry very much. There is, well, I was with this Daimler-Benz company, and unfortunately, two of the most famous and most expensive software faults were on my company. One fault was the start of Ariane 5. Ariane 5 is a rocket bringing things up into the space. And they had the Ariane 4, the model before, 5, and 5 was constructed to bring larger amounts of stuff into space and to bring the Hermes European space shuttle. It was planned like that. The first flight of Ariane 5, maybe 30 years ago, it started, a beautiful flight, and then it turned, and then it was self-destroyed. So they thought, if we have time at the end, I will show you the film. You will remember it. And about 1 billion euros were gone. And they found an error. The error was quite simple. I know the colleagues from there. They took the software of Ariane 4 and put it on the Ariane 5. So they tested and tested and tested, and they thought everything's fine. There was one small problem. There was already an error in the software, but it didn't occur. Ariane 4 flight well all the time. Ariane 5 was constructed different, so the program were executed differently. And it came to this place where this error was. This error was that because we are on the southern hemisphere, the orientation of the rocket is different than it was started on the northern hemisphere. So because of that, the rocket thought, oh, I'm wrong, I'm flying the wrong direction, and it turned. And then the other software system worked, and it realized that they are going in the wrong direction, and it destroyed the rocket. 1 billion euros gone. A nice firework. I will show you that. Or do you want to see it now? I can try to find it. It's on YouTube. So it's free. You can look at it. It's, yes. There's no sound. They counting down 13, 12, 11, 10, 9, 8, 7, 6. Some audio and the beginning it was quite fine. Software error. Simple software error. Yes. Usually they have a big party after that. But that day there was no party. Okay. Some people on the beach. It's in South America, it's in Cove Road. French Guiana, north of Brazil. Yes. It was a big shock because search for the rocket and try to find what was the reason for it, yeah. But at the end, it was not a hardware problem; it was just a software problem. If they would have started it in Florida, nothing would happen. The problem was exactly that they tested it for northern hemisphere and not for the southern. Okay, we can laugh about it because it's just a rocket. I will tell you another thing. Not so funny. Okay, yes. Sorry. Yes. When you have to see it again. What is the story behind it? If a company like Airbus or Boeing wants to sell planes, especially new ones, the Airbus A320 was a new airplane at that time. And this was a presentation show for companies who want to buy this airplane. Okay? They're sitting Arabs, Chinese, Brazilians, plenty of people, companies who want to buy this Airbus. And they could see how they wanted to show how good this airplane was. So then, what happened? It started and now it has to land, okay? At the end, every airplane comes to the ground. What happened here? The pilot wanted to show a special maneuver, which is if there's something wrong, and on the airplane, he can start again without being landed. You can see it's going down. At this time, everything was fine. instead of going down, we wanted to move up. And you can see that didn't work. He could not land anymore, so he tried to bring the airplane up, but it didn't work. So what was the problem? The problem was they had another man-machine interface into this airplane. So the idea was that the pilot has not a lot to do anymore. But they hadn't tested, obviously not properly, when this special situation is arising, that you have to want to land, but then for any reason you have to start again without being landed. So the plane said, I want to land, which was the original plan, and it was not possible to change the plan. The pilot tried to bring it up, but it didn't work. The software did prevent him from doing this. So at the end, he crashed into this forest, and the team inside the plane died. So it was an absolute disaster. And only 4 people dead, because then only the pilot, the co-pilot, and I think 1 or 2 more. So only 4 people in the plane, but of course they were dead. And the situation was for Airbus very difficult, because they had to find this error. It was a software. So in both cases, they did not test properly. In the first sense, they did not test the southern hemisphere situation. And here, they did not test this situation when you try to land and you cannot for any reason, and you have to go up again. So this new software, which should help the pilot, it obviously worked wrong. If they changed it, of course, you can change errors, but of course, 1 plane gone and 4 people dead. So it was another disaster at that time. Okay, why are they so well documented? Because Airbus is partly a public company. Some shares belong to the French state, some shares belong to the German state. So the state says we want to know what's going on, and you have to publish it. Usually companies who have problems, of course they try to find the error, but they don't tell about it. Yeah? They try to keep it down. Okay, so from these 2 cases, I tell you, we know there are errors in the software. And I can tell you that I know this company quite good. I started to work with Mercedes-Benz, a car company. Then I moved to the research center, central research. I started to do research for Mercedes, but at the end, I got another position. I was responsible for projects for Airbus, the space part of the company. So I know the colleagues quite good who worked on that software. Not everyone, but some of them. Yeah, so it was a sad situation. They fixed the error, but of course you are not happy if you lose people and if you have things like this to happen. The problem was at the time the pilot was not allowed to do this. He just had to land. No one, we cannot ask him anymore. Why did you try to bring it up? Yeah, it was a bad decision. Usually you do it not when there is a forest at the end of the landing. You do it where you can have plenty of space, and you can, if something's going wrong, you still can bring the airplane down, or the airplane down, or can have possibilities to start again. Okay. 2 bad errors. Okay. So if debugging is fine, debugging, the precondition is you know that there is an error, and you have the error did something wrong. So you know there is an error, and now you have to find it and you have to change the code. Testing is finding errors. So I have to say testing first and then debugging. Yeah? Testing and the answer, testing is to prove that the program is correct. It's the complete wrong answer. Testing is to find as many errors as possible, because we know there are errors in the software. We try to find them, we try to remove them, and yes, we hope that there are after testing and debugging and correcting we have less errors in the software. So testing is the process of program execution with the intent to find an error. So a good test is one who had a big Wahrscheinlichkeit is probability to find an error not yet discovered. Yeah? When you say, okay, I tested it and everything went right, okay, but a good test is one when you said, I found an error, because we know there are errors in the software. Test. So a successful test is one who has found an error. So testing is a destructive process. We don't like it very much, because testing shows the existence of errors and never their absence. Yes? The most important message today. Testing is a process that you want to find errors. Even you believe your software is perfect, you have to try to find errors. So here is, unfortunately, it's German. First is testing, then you evaluate the results of the tests, and then you have the errors, and the errors with debugging, you try to localize them and to find where they exactly are and to correct it. Here it is what they call reliability modeling. In all these software systems of Airbus and the space part of the company, they do modeling of reliability because they test absolutely a lot, really a lot. I know plenty of companies who do testing. I can say I know no company who is testing more than especially Airbus and the other space things, because it's so much money involved and there are people involved. So you need to test a lot. And you have to code very well. So software development in these areas is very expensive. Okay. You have different phases of the software: requirements analysis, specification, system design, module design, programming. And related to each of these activities, you have a relevant test. You have acceptance testing by the users, you have systems tests, integration tests, and unit testing. This is what students do mostly of the time do. They test their modules. You don't do integration tests and systems tests because your software is not big enough to do that. But companies have to do that. Okay, when do we have the wrong, sorry, I have the wrong version. No? Give me a second. No, sorry. Here we have to go with it. So, usually you have a problem or you have a task, you have to think you can solve it with the software. So, plenty of people do just quick and dirty programming. They just start to program and they have a program. Okay. Software engineers do other things. They first do an analysis of called requirements engineering, then they have a specification. Specification tells you what is to do. Then you have a design, and the design is how is it realized, and then you do the programming and you have the result of the programs. So we are talking about software design. When do we generate test cases? There are two places in this where we generate test cases. One is here at the end of the specification, somewhere here in between, before we design. We do something what we call a test to specification. We have a black box test. I will tell you what is later how we do that. But we test the specification. We still have no line of code, but we generate test cases which will later be used to test the programs. So a test is done. If you start to program and there is no test case, then something is wrong, because you have done no black box tests. Yeah, my students who do something and they start to, I see they started to program in their projects. I go to them and say, okay, tell me your test cases, your black box test cases. And sometimes the students say, because they haven't done it yet. Okay, tomorrow I come again and I want to see the test cases, and they work on it, and it works. Yeah? Because if you start to program, then you have a different view, a completely different view to the test cases. Then you generate what we call white box testing. So after the design, you start to program, and white box testing means you can see the code, and the testing is to the code, not to the specification. Completely different systems of testing. Completely different. Okay. Yes, black box is here, white box it's during programming. We already had that. Okay, an example. Sometimes I gave it to the students. I say, okay, we write a program, and the program has an input of 3 integers. Let's say 3, 4, 5. Okay? 3 numbers are to be interpreted as length of a triangle. Very easy. So, the program produces an output indicating whether the triangle is equilateral, isosceles, or unequilateral. So we have 3 sides the same, 2 sides the same, the third one different, or all 3 different. Okay? So how many test cases are needed to adequately test this small program? What would you think?
I think one test should see if any input is negative.
Okay. And is it as a negative number?
Yes.
Okay. What test cases would you generate?
If the angles, if you, but you don't have angles.
We have no line of code yet. But we generate test cases for small problem.
If the length doesn't match any of these.
Okay. Okay, because we have, unfortunately, not so much time, I will give you a short view how many test cases it may be. It's a program of nothing, yeah? It's nothing. So we have something like this, -1, -4, 6. And you say the answer is no, it's not a triangle because negative things. 1, 1, 1, yes, it's a triangle and all sides are equal. 3, 3k, it's wrong because here is not an integer. 2, 1 and nothing, it's wrong because you need 3 integers. Something like p, well, the answer is only integers. 5, 5, 10, very difficult. Because it looks fine, but it is not.
It's not a triangle.
It's not a triangle, it's nothing. It's no, exactly. 3, 4, 4, it's a It's a triangle, yes, two sides are equal. 5, 5, 11, similar to this one, but not the same. Wrong. 3, 4, 5, okay, yes. And then you have permutations of all input. Just for one of these. 3, 4, 5 is, you have to test 4, 5, 3, 3, 5, 4, 4, 3, 5, 5, 3, 4, 5, 4, 3. So one test case you have here in this really small problem, you have 6 test cases. Okay, shall we do it? Shall we work like this? No, we shall not. Because it will destroy our lives. Because we would test till the end of eternity. Because usually programs are much bigger than these small triangle programs. So we have to find an engineering way how to generate good test cases, but not too many. You have to cover the area of testing quite fine. Okay, look at the functions of the systems and show them working correctly as well as incorrectly. We call it black box testing. Functions are black box, and we just put something in and we get something out, and we say, okay, it's right or wrong. Black box or functional testing. No code. We don't look at the code. We look at the internal structure and processes and make sure that each internal function works as specified or show that it's incorrect. If we really look at the code, we have completely different test cases, and we call them white box or structural testing. I think you have had a programming course here in the university. What do they learn? C# or what do you learn here in programming course?
C, C++, C#, and maybe Java,
Okay.
and Python.
Okay.
Many
languages. Okay.
assembly.
Okay. So you have a different way of learning how to program. We have the idea that we think it's better to learn to know one language very well. Then you can move this knowledge to other languages instead of learning 5 or 6 or 10 languages, everything in just a little, because your time is limited. Yeah? If you learn 6 languages and you can spend, let's say, 5 weeks on each language, it's 30 weeks. But if you can spend 30 weeks on one language, you know everything about it. We have the idea that all students should learn Java. And now we are changing a little bit. Now we have introduced Python, because we need it for data science. And what do we need? Oh, what else do we need? I think one colleague is doing C++ because he's doing the computer graphics. He's a computer graphics guy. Java is not so common in computer graphics. Okay, so we have the C++ graphics professor, and we have the artificial intelligence people who use Python. But it's very limited, we have only 3 languages. So, what is the idea of black box testing? Okay. In black box testing, we know sometimes there will be a system, our developed system. We have a large set of possible input data. Now, we say, okay, if we have here inputs causing anomalous behavior, a subset of these all possible input data, and we put it into the system, we have on the output side the presence of errors. So we say this set of input data is related to this set of output data. So now the idea is if we say, if we take one test case out of this large group of possible test cases, then he's a representative for all the others. Okay? So we have to find these sets of input data related to each other. There's another one, and here, always large groups of input, possible input data related to some set of output data. If you take only one per group, to reduce the number, I will give you an example, reduce the number of possible test cases. Not to have this situation that with a small program, you have to test and test and test, and nothing is changing it. Okay, black box testing is also called functional testing, data-driven testing, input-output testing, behavioral testing. Over the years, different words were used for this kind of testing. The tester sees a program as a black box. Don't look inside the code. No information is given you about the internal structure of the module. The test data is derived exclusively from the specification. So we call it test to specifications. To find all errors in the module, countless test cases would have to be executed. Since this is impossible, it follows black box testing cannot guarantee that a program is free of errors. No testing situation can guarantee it. The program is free of errors. So the focus is on economic testing. That is, as many errors as possible are to be found with a limited number of test cases. Yeah? So to go back, just a minute. If we look at these solutions, some test cases, it doesn't make sense to have these 6 test cases and all the others not. And you say, okay, I did a lot of testing, here are my test cases, and everything went right. The idea just to see is that I take one of these 6, I take one of this, 2 sides are equal, I take one of these, all sides are equal. Then I have all these special cases, a very interesting one. This one, you have to be, and you have to test all these strange things, minus, strange words, nothing. But at the end, you have a subset of all these test cases. We will see. Okay, what can be found if we use black box? Faulty and missing functions. We are testing test to specification, so in the specification you have the functions defined. If they are not there, we will find them. We hope. Interface errors. Errors in data structures and data access. Performance error. Because if you have a situation that tells you that some software has to be as fast as this, you can find. Initialization and termination errors can be found as well. We have some black box, very important black box testing. What do you say? Testing, generating testing cases. And I will just talk about 2 of them. One is equivalence partitioning, and the other is boundary value analysis. There are a lot more, especially this one is a nice one, error guessing. If you have an experienced programmer like Cesar Posa is, and you have a large program, you would ask him, okay, Cesar, you know the program a little bit, you know the situation, what I have to program. Tell me, where would you expect are errors in the program? He would think a little bit about it and said, okay, I think you have to look there and there and there. I think if you have errors in the program, there are these places. And the reality says that the best to find errors and to correct errors, anything, is to ask an experienced programmer. Testing is so difficult that experienced programmers have the best results if we talk about errors. But that doesn't help you because you are not an experienced programmer. You need other things to do. So the 2 best versions is this equivalence partitioning and boundary value analysis. Already we have this. We have this input, invalid ones, valid ones. And you have the system, you put these test cases in it, and it's generating output. So we always have the idea that a set of similar test cases, we take one out of it, will come to a result here, and if we take any of these groups, it will come to the same output set. Now we have an example. Will it come? Yes, there's the example. We have a possible number of input values. And here are 3 equivalence classes. One is less than 4, one is between 4 and 10, and the next one is more than 10. So you have to take one out of each group, one representant of each group. So this is the 3, the 7, and the 11. Okay? The second thing is that you have, you call it in English, boundary value analysis. The boundaries are this one. At the borders, the boundaries of the equivalence classes. And so you need to test the 4, and you need to test the 10. You get the boundaries as well, because boundary errors are quite happening often. Okay? If you look at a similar problem, less than 10,000, between 10,000 and 99,999, and more than that, it's similar. You have one each, and you have the boundaries as well. So let's test now. We have 12 months, and usually you have an integer field, and in this integer field there can be the numbers 1 up to 12. Nothing else. So what are the equivalence classes for that? First the classes, then the boundary values.
0, 1, 12, and 13.
0. Okay, let's first define the classes. The first class is 1 up to 12, including 1 and 12. That's the correct class. Then you have the class above 12, 13 and more. Then you have the class below 1, 0, and minus 1, maybe. Now you have to take 1 out of each class. So you can take the 0 and the 1 you said. 1 is boundary. Then you have the 12 and the 13. And you have to take, usually, take 1 more from the correct words. You need, let's say, 6. Okay, so it's 5 cases. And more. Okay, you have to test all these all these wrong, completely wrong things, like nothing or literals or whatever. You know? But from the equivalence class, it's exactly that. So you can reduce. You have an idea how to test the program. It's the main point. You have an idea. What are the equivalence classes? What I have to test, and then you can create the test cases. So it's nothing more you have to know. Yeah? You have to build the classes. You have to take one representant out of each class, and you have to look at the boundaries. That's it. And you have to call, of course, you know, this input, what is the expected output? Because if you just say, okay, I have to test 4, you test 4, and there comes an output, and you say, okay, it's right. Maybe it's not right. You have to define the output before you test. Yes. What is now very common, when I started with Daimler, I programmed a small automated automatic testing. We had to test a large information system, and we had data from the people who wanted to use the system. And so I programmed something where we put the data into a database, the test data. And in the evening, when we had finished our work, we made an increment of the software. Then we loaded the test data into the system. Over the night, we let it run. And in the morning, we got the results, where there are errors. So at the beginning, it was absolutely fantastic. We found lots of errors. And because it ran over the night, in the morning we had the nice view on our system, what we did wrong. So we corrected the errors, and over the time, we had very little errors, very little. But then arose the problem. We had little errors, but the system obviously didn't work well. Do you have an idea what happened? Especially the older colleagues blamed me, and they said, yes, you have made this system, but you can see it don't work because we have more errors, even more errors every day, and your system is not producing, not showing us that these errors are there. You can write as many test cases as you want. You will never cover all errors. Never. You only have a part of it. So over the time, you will have system still many errors in it, and some of these errors will occur during other tests or during using the system. So they said you are wrong. It was just a funny program from someone coming from university and tell us how to develop software. And I said, okay, let's do a different thing. I will put 10 errors in the program. I put 10 errors in the program, in somewhere. We don't know where. And then we test the program. And out of the tests, I found maybe 5. And 5, this automated testing system didn't find. So I said, okay, you see, 5 false errors can be found, but 5 cannot be found. So there are not enough test cases for it. We need to generate other test cases. And so they generated other test cases, and we found plenty of errors more, but you never will find all the test cases, all the errors, never ever. Now we come to a completely different way of testing. I just have 10 minutes, so I will do it quite quickly. White box testing. Now you have finished your code, and you can look at the code. We test the code. So if Professor Poser is giving you a task to get a certificate for programming, of course he will. I'm sure he will. At the end, he will test your programs, or not. Is the professor looking at your programs and test it? His test data? Yes. He does it, I do it, all professors do that. What test cases do you think he's using? Black box or white box?
White box.
I think black box. Because he can use his test case for all of your programs. White box test would mean that he had to generate 3 different test cases. He had to look at your special code and had to design a test case related to your special code. Much different, but you cannot do that. If you have 50 students there, he's coming with his black box test cases and he can use it for every program. If it's white box testing, you have to write at your code, a lot of time, look at your code, then to generate a test case related to your special version of the program. So white box testing is completely different from the thinking, from the way we do tests. Okay, let's look at it. It's also called structural testing, logic-driven, path-oriented. Tester views the program as a glass box, can look into the code. The test data is derived from the program logic. We test the code. Executing each statement may already require extensive testing. Look at it. For every statement, you test every statement just once. Execute one statement may require extensive testing. Executing all paths in the program leads to exhaustive testing. So it exhausts the system developer. Really, believe me. To find all errors in the module, countless test cases would have to be executed. And during the time you have developed the software further and further and introduce new errors. So you can never come to a point where everything's correct. Moreover, logical errors would not be detected in the process. So what do? We have a combination of black and white box testing if you're a serious company. What can we find with white box? So just as path errors, condition errors, if then else, data flow errors, and loop errors. An interesting point is the loop is not executed n times, but n plus 1 time or n minus 1 times. Classical problem. Okay, we call it the path coverage testing. Okay, we have different strategies to cover the statements. The most easiest one is path coverage of each line of code. And the others are quite more to do. I will just give this, we'll look at this. So this is a small flow chart. And if you look at this flow chart, it looks very simple. Unfortunately, here's a nice condition. This loop is executed up to 18 times. So you have to test it for 1 time, 2, twice, 3, 4, 5, 6, 7, and in combination with other execution in this this part of the software. So we have more than 10. I don't know how 10 multiply with 10 with 10 multiply 12 times. So you cannot do that. Even for this model, cannot test all paths. You cannot. So what is the most easiest one? The most easiest one is line coverage. Line coverage doesn't look at the instructions, but only at the executable source code lines. So if false, print, covered. That will result in a line coverage score of 100%, while the syntactically and semantically identical but differently formatted program, if, else, print, covered, would only lead to a line coverage in 50%. Okay. So the simplest coverage statement is the coverage, statement coverage, also called C0 tests. Each statement is tested at least once. In this way, they will ensure that there's no dead code. There are no instructions that are never executed. They do exist in the program. If you remember the Ariane example, they obviously didn't test this part of the program, which at the end resulted in a destruction of the Ariane. So statement coverage would have solved the problem. But they did not do that, because they used it already in Ariane 4, and they thought everything's fine. Okay, if every instruction in the program has been executed at least once, it is called complete instruction coverage. Okay. Yes, for instance, if you have this small problem here, it's sufficient to test all nodes in the control flow graph. Then you have a statement coverage. You can look at it, it's not complicated. I will come to the next one, because the next one is the most used coverage system. I will just leave it here. Okay, here is an example. Statement coverage can be reached with only one test case. We start here. 1, 2, 3, 4, 5. Start. Okay, then you have executed every line of code. If in these boxes there are lines of code, if you go this way, you have executed each statement at least once. If there are no conditions inside these boxes. The second is the most used in this part. It's the branch coverage. This is the last one I will tell you because we are coming now at the end. The branch coverage test runs through all branches. The branch overlap test is also called the decision overlap test case because the auxiliary variable must be run through at least once with the value true and false. In this case, the while loop must be run through at least once. This is one. Traversing the branches also ensures that each node, each instruction is executed at least once. So branch coverage does include code coverage. This is a little bit more. Well, the point is, how many test cases do we have to generate if we have a problem like this? We can look at flow graphs. We have here an if then else execution. If true, then go here. If false, then go here. Then you have to bring it together. Here's a loop. We don't know how many times. And here's a case statement. So if you look at operations, mainly these three structures do occur if you have decisions to make. So we have now this, this flow graph, and we have to know how many test cases do we want if we cover all paths. And there was a mathematician, gave us a solution for that. And it's called the cyclomatic complexity. And it's coming from an American mathematician called McKay. So we have the McKay cyclomatic complexity, and it is, you can count it. It's the number of edges in the control flow graph, and the number of vertices in the control flow graph, and what is called a program factor. And you can count these, you can put these values into this formula, and you get a number out of it. And this number is the number of independent paths. So if you want to have a path coverage, you have to generate exactly as many test cases as this formula will generate, but of course the right ones, not wrong ones. So maybe have an example. Okay, I hope I have the right example. We have 4 linear independent paths, and if all independent paths have been processed, then each statement has been executed at least once, and each branch is executed with true and with false conditions respectively. So a good integrated development environment is telling you what is a cyclomatic number. And today you have if you have a very good tool, it will give you advices how to generate these test cases related to the cyclomatic number. I will just want it. Okay, now it's a little bit disastrous. What are the advantages? We have branches that cannot be reached. We have an error detection rate at approximately 33%. So 66 are still in the software. A fifth of these are calculation errors, the rest are control flow errors. What are the disadvantages? Dependencies between conditions are not taken into account, loops are insufficiently tested, and complex branching conditions are only weakly tested. Okay, we have just this example to tell you how many test cases do we need. Here we need 2. One is for we already had. 1, 2, 3, 4, 5. Stop. The other one is 1, 3, 5. Stop. And you have covered all these vertices. 2 test cases. We don't know whether the program is correct, but we have a structure of testing. We not just did something, we just have a serious engineering working on testing. There are plenty of other path coverage testings. And I can tell you, I was with this aerospace company, and I can tell you that this is just for the universities, just to know it. They don't do it. They are the best testers I know in the world. Even they did these errors. But you cannot spend so much time doing this. So the hope 30 years ago was that one day we have two things. We have computers that are faster at the time 30 years ago. And the second is that we have an artificial intelligence who is doing the testing for us. And I think this will come in the next 10 or 20 years. So testing will be done by an artificial intelligence. And it is running through the nights in the computers, and in the morning you have a result of it. 5 minutes late, sorry. Any questions? So I resume. The most important thing you have to take with you is testing is not showing that the program is correct. Testing is to find errors. You should be happy if you find an error, because then you can correct it. If you don't find it, it's still in the program, and it will cause problems later. So don't be afraid to find an error. Just be happy that you have find one. Second is, if you have to test, and you have to test, take these things to generate you serious and good test cases. So you need to test the specification before you write the code, and you can use these path coverage, the cyclomatic number that generate test paths that you test. And even then, there are still, after you found the errors, after you corrected them, and you did the same with the tests, there are still plenty of errors in your program. Unfortunately, it's like that. So sometimes, yes, you will get gray hair. All computer scientists have gray hair when they grow older. Because of finding, or not finding errors in the program. Okay. Thank you very much for listening.